The concept of quantum foam, which is a fascinating idea in the field of quantum gravity, suggests that at the tiniest scales of space and time, the fabric of the universe is not smooth, but rather it is a turbulent sea of fluctuations, which can be thought of as a sort of foam. This foam is theorized to exist at the Planck scale, which is around 10 to the power of 35 meters. Far smaller than anything we can currently observe. This idea stems from the principles of quantum mechanics and general relativity. As physicists try to unify these two major theories, when we think about space-time, we often visualize it as a smooth continuum, but quantum foam presents a more chaotic and dynamic view of the universe where tiny bubbles of space and time can appear and disappear almost instantaneously. One of the most intriguing implications of quantum foam is its potential effect on the very nature of gravity, as it suggests that space-time is not just a backdrop for events, but rather an active participant in the unfolding of the universe, with its own properties that can fluctuate and change. These fluctuations might influence the paths of particles as they travel through space-time, leading to phenomena that challenge our traditional understanding of causality and the flow of time. This concept also raises questions about the nature of black holes, as the extreme warping of space-time near these objects could be influenced by the quantum foam, possibly leading to new insights into their behavior and the information paradox that surrounds them. Furthermore, quantum foam may have implications for the early universe, particularly during the moments immediately after the Big Bang. In this chaotic state, the fabric of space-time could have been a tumultuous landscape of bubbles, where the laws of physics as we know them start to break down, leading to a period of rapid expansion known as cosmic inflation. This inflationary epoch might have been influenced by the characteristics of quantum foam, suggesting that the seeds of large-scale structures in the universe could have been planted in this frothy quantum landscape. In addition to its theoretical implications, quantum foam has also sparked interest in experimental physics, as scientists look for ways to test these ideas. One avenue of research involves examining high-energy cosmic rays and their interactions with the universe. Some researchers hypothesize that if quantum foam exists, it could cause observable effects on the paths of these particles, leading to signatures that might be detectable with advanced instruments. This kind of experimental evidence could provide a window into the fundamental nature of space-time, potentially confirming quantum foam. A fascinating concept in the realm of quantum physics refers to the idea that at the smallest scale, space-time is not smooth and continuous, but rather fluctuates wildly, resembling a frothy bubbling structure. This concept suggests that at extremely small scales, like the Planck length, which is around 10 to the power of 35 meters, space-time is subject to constant change, with tiny virtual particles popping in and out of existence, creating a sort of chaotic sea of energy. The term quantum foam was first proposed by the renowned physicist John Archibald Wheeler in the 1950s as he explored the implications of quantum mechanics and general relativity. Wheeler's idea emerged from the realization that the fabric of space-time might not be the stable backdrop we perceive in our everyday lives, but instead a dynamic, ever-changing medium influenced by the uncertainty inherent in quantum mechanics. This notion challenges our classical understanding of the universe, suggesting that on the quantum level, the very structure of space and time could be influenced by the activity of matter and energy, leading to a fundamental rethinking of how we understand the cosmos. In simpler terms, imagine space-time as a vast ocean, where instead of calm waters, you have waves and bubbles, constantly forming and collapsing. This perspective opens up exciting possibilities in theoretical physics, as it implies that the universe is much more complex and intricate than it appears to us at larger scales. The concept of quantum foam also leads to intriguing questions about the nature of black holes, the Big Bang, and the ultimate fate of the universe, as it invites scientists to consider how these seemingly distant phenomena might be connected to the fundamental fabric of reality itself. Wheeler's contributions to this field have inspired countless physicists to delve deeper into the mysteries of quantum gravity. And while quantum foam remains a theoretical concept, it plays a critical role in our ongoing quest to understand the universe at its most fundamental level, merging the realms of quantum mechanics and cosmology in a way that challenges our existing frameworks of understanding. As researchers continue to explore these ideas, the implications of quantum foam may hold the key to unlocking some of the most profound questions in modern physics, leading to a deeper comprehension of how everything in the universe is interconnected, even at the smallest scales. Quantum foam, a term coined by physicist John Wheeler, refers to the concept that at the smallest scales of space and time, the fabric of the universe is not smooth, but rather it is a turbulent, frothy sea of fluctuations. This idea arises from the principles of quantum mechanics, which govern the behavior of particles at the microscopic level. Quantum mechanics tells us that particles do not have definite positions or velocities, but instead exist in a state of probability described by a wave function. When you look closely at the fabric of space-time, especially at the Planck scale, which is roughly 10 to the power of 35 meters, you find that the usual smoothness of space-time gives way to chaotic fluctuations. These fluctuations can be thought of as tiny bubbles or foam, constantly forming and disappearing, creating a dynamic and ever-changing background. This concept of quantum foam is directly related to the uncertainty principle, which states that the more accurately we know a particle's position, the less accurately we can know its momentum, and vice versa. Essentially, at such small scales, the energy and the geometry of space-time are intertwined, leading to a scenario where the very structure of the universe is uncertain and fluctuates wildly. In quantum mechanics, the vacuum is not empty, but is filled with virtual particles popping in and out of existence. Quantum foam can be seen as an extreme manifestation of this phenomenon, where the vacuum fluctuations create a kind of bubbling effect. This relates to the principle of superposition, where particles can exist in multiple states at once, and it suggests that space-time itself may be subject to similar rules, existing in various configurations simultaneously. As physicists try to reconcile quantum mechanics with general relativity, the concept of quantum foam becomes increasingly important. It hints at a deeper, more fundamental structure of reality, where space-time is not a fixed backdrop, but a dynamic participant in the universe's behavior. This has implications for theories of quantum gravity, which seek to unify the principles of quantum mechanics with those of general relativity, and quantum foam may provide insights into how gravity operates at the quantum level. Thus, quantum foam serves as a bridge between the microscopic world of particles and the macroscopic world we experience, revealing a universe that is far more intricate and interconnected than our everyday experiences suggest. The uncertainty principle, formulated by Werner Heisenberg in the 1920s, plays a significant role in the fascinating concept of quantum foam, which is an essential aspect of quantum mechanics and our understanding of the universe at its smallest scales. At its core, the uncertainty principle states that it is impossible to know both the position and momentum of a particle with absolute precision at the same time. The more accurately we know one, the less accurately we can know the other. This idea has profound implications for the behavior of particles at the quantum level, where the traditional laws of physics begin to break down and give way to strange, counterintuitive phenomena. When we talk about quantum foam, we're referring to the idea that at the Planck scale, which is about 10 to the power of 35 meters, the fabric of space-time is not smooth and continuous, but is instead frothy and turbulent. This foamy structure arises from the inherent uncertainty present in the quantum world, leading to fluctuations in energy and the creation of virtual particles that pop in and out of existence. These fluctuations are a direct consequence of the uncertainty principle, as the energy of a system can vary within limits, even when no real particles are observed. To visualize this, think of the quantum foam as a bubbling surface, where tiny bubbles represent virtual particles that are allowed to exist for fleeting moments due to the energy-time uncertainty relation, which states that the uncertainty in energy multiplied by the uncertainty in time is on the order of Planck's constant. This means that, for very short periods, the energy of a system can deviate significantly, allowing for the temporary existence of particles that would otherwise be forbidden by the conservation of energy in classical physics. The presence of this quantum foam has implications for various phenomena, including the nature of black holes and the behavior of space-time itself. For instance, at the event horizon of a black hole, the extreme gravitational forces and the uncertainty principle can create conditions where quantum foam becomes incredibly significant, leading to potential insights into the nature of gravity and quantum mechanics. Moreover, quantum foam is hypothesized to contribute to the fluctuations in the cosmic microwave background radiation, which is the afterglow of the Big Bang, influencing the formation of large-scale structures in the universe. In essence, the uncertainty principle is not just a quirky aspect of quantum mechanics, but rather a fundamental feature that helps shape the very fabric of reality, allowing for a universe that is dynamic and constantly in flux. Rather than a space-time is a fascinating concept in the realm of physics, particularly within the framework of general relativity, which was developed by Albert Einstein in the early 20th century. To understand space-time, you first need to think about how we perceive the universe. Traditionally, we view space as three-dimensional, consisting of length, width, and height, while time is seen as a separate, linear progression. However, Einstein proposed that these two ideas are intertwined, forming a four-dimensional continuum known as space-time. In this four-dimensional construct, space and time are not independent entities. Rather, they are interdependent. This means that the position of an object in space is linked to a particular moment in time, and changes in one can affect the other. For example, if you were to observe a star, your perception of its position is tied to when you look at it, because light from that star takes time to reach you. Thus, the concept of space-time helps us better understand how objects move and interact in the universe. One of the key elements of general relativity is the idea that massive objects, like planets and stars, actually warp the fabric of space-time around them. You can think of space-time as a stretched sheet or a trampoline. If you place a heavy ball in the center, it creates a depression in the sheet, causing smaller balls placed nearby to roll towards it. This analogy helps illustrate how gravity works according to general relativity. Instead of thinking of gravity as a force pulling objects together, Einstein described it as the result of the curvature of space-time caused by mass. So, when you see an object falling towards Earth, it's not just being pulled by gravity. It's following the curved path in the warped space-time created by Earth's mass. This concept leads to some intriguing implications, such as the idea that time is experienced differently depending on the gravitational field you are in. For instance, time passes slightly faster for someone on a high mountain compared to someone at sea level, due to the weaker gravitational field at higher altitudes. This phenomenon, known as gravitational time dilation, has been confirmed by experiments that show atomic clocks at different elevations tick at slightly different rates. Additionally, space-time allows for the possibility of theoretical constructs like wormholes, which are shortcuts through the fabric of space-time that could connect distant parts of the universe. While these remain speculative and are not yet proven to exist, they arise naturally from the equations of general relativity and spark the quantum foam. A concept arising from quantum mechanics introduces a fascinating layer of complexity to our understanding of space-time, challenging the classical notions that have dominated physics for centuries. At the heart of this idea is the notion that, on the smaller scales, space-time is not smooth and continuous, as we often picture it, but rather a frothy, turbulent sea of energy fluctuations. This concept was famously proposed by physicist John Wheeler in the 1960s, suggesting that at very small scales, such as the Planck scale, the fabric of the universe is filled with tiny, ever-changing bubbles, or foams, which can fluctuate in size and energy. In classical physics, space and time are viewed as a smooth, unchanging backdrop against which events occur, following the principles laid out by Einstein's theory of relativity. However, quantum foam implies that space-time itself is dynamic and subject to change, reflecting the uncertainty that is inherent at the quantum level. This means that the very structure of space and time can be warped or distorted by quantum events, leading to a fundamental rethinking of how we understand gravity and the forces that govern the universe. One of the most intriguing implications of quantum foam is how it might reconcile the seemingly incompatible theories of general relativity, which describes gravity as a curvature of space-time caused by mass, and quantum mechanics, which governs the behavior of particles at the smallest scales. The idea that space-time is not a rigid, fixed entity, but rather a fluid, ever-changing landscape suggests that there may be new physics at play, possibly leading to a unified theory that could bridge these two pillars of modern physics. Moreover, if quantum foam exists, it opens up questions about the nature of black holes and the behavior of particles near them. For instance, if space-time is indeed foamy, the singularities predicted by black hole theories might not be the point-like infinities we once thought, but rather regions of highly fluctuating space-time, where the rules of physics as we know them break down. This could have profound implications for our understanding of information loss in black holes as well, challenging the classical idea that information is irretrievably lost when it crosses the event horizon. In addition, quantum foam might also have implications for the study of cosmic inflation, the rapid expansion of the universe that occurred just after the Big Bang. If space-time was indeed foamy during that time, it could help explain some of the observed uniformity of virtual particles. Are fascinating entities that exist within the realm of quantum mechanics, often described as temporary fluctuations in energy that pop in and out of existence. These particles are not directly observable, but their effects can be measured, and they play a crucial role in the understanding of fundamental forces and interactions in the universe. In quantum field theory, virtual particles arise in the context of interactions between real particles. For instance, when two electrons interact, they can exchange virtual particles such as photons, which are the carriers of the electromagnetic force. This phenomenon illustrates the concept of virtual particles being part of the underlying fabric of the universe, where they contribute to the forces that govern the behavior of matter and energy. Now, when we talk about quantum foam, we're diving even deeper into the quantum world, where the very structure of space-time is thought to be dynamic and constantly fluctuating. Quantum foam is a term that was coined by physicist John Wheeler, and it refers to the idea that at extremely small scales, specifically at the Planck scale, space-time is not smooth and continuous, as we perceive it at larger scales, but rather it is turbulent and frothy, like a boiling liquid. In this quantum foam, virtual particles are constantly being created and annihilated, leading to a chaotic environment where particles can briefly exist, impacting the fabric of space-time itself. This means that on the quantum level, the universe is a seething mass of activity, where these fleeting particles contribute to the energy fluctuations of the vacuum. This interplay between virtual particles and quantum foam suggests that the vacuum is not empty, but rather a rich tapestry of potential activity, where the properties of particles and forces emerge from this underlying chaos. Moreover, the concept of quantum foam has implications for various theories in physics, including those that attempt to unify quantum mechanics with general relativity. It raises intriguing questions about the nature of reality, time, and space. As researchers continue to explore the implications of quantum foam, we gain insights into the fundamental workings of the universe, uncovering the unexpected connections between the microscopic world of particles and the macroscopic universe we observe. The study of virtual particles and quantum foam represents a frontier in our understanding of the universe, challenging our perceptions and expanding the boundaries of what we know about the nature of existence itself. Quantum foam, a concept in quantum mechanics, suggests that at the smallest scales, the fabric of space-time is not smooth and continuous, but rather is a frothy, chaotic sea of fluctuations. This idea arises from the principles of quantum theory, which tells us that energy can never be completely at rest, even in what we perceive as empty space. In fact, according to Heisenberg's uncertainty principle, there is a limit to how precisely we can know both the position and momentum of a particle, which leads to the notion that energy levels in a vacuum can fluctuate wildly, creating temporary particles that pop in and out of existence. These fluctuations occur on incredibly tiny scales, around the Planck length, which is about 10 to the power of 35 meters. The concept of quantum foam was first introduced by physicist John Wheeler in the 1950s, who proposed that on these minuscule scales, the very geometry of space-time is dynamic, constantly changing due to these energy fluctuations. These fluctuations imply that even in what seems to be a complete vacuum, there is a constant buzz of activity, with virtual particles appearing and disappearing in a fraction of a second. The implications of quantum foam are profound, as they suggest that the vacuum of space is not truly empty, but rather filled with fluctuating energy that could have various effects on particles and fields. For instance, this fluctuating energy may contribute to phenomena such as the Kojima effect, where two uncharged plates placed very close together in a vacuum experience an attractive force due to the restricted wavelengths of virtual particles between them. This effect has been experimentally verified, highlighting the tangible consequences of what might otherwise be dismissed as abstract theory. Moreover, the implications of quantum foam extend into areas such as black hole physics, where the extreme conditions could lead to significant fluctuations in energy and matter, potentially affecting the information paradox associated with black holes. In the context of cosmology, the idea of quantum foam could also play a role in the early universe during the Big Bang, where quantum fluctuations might have contributed to the large-scale structure of the cosmos we observe today. Therefore, quantum foam represents a crucial intersection between quantum mechanics and the nature of space-time, suggesting that the universe is a much more dynamic and vibrant place than our everyday experiences might lead us to believe. The existence of fluctuating energy in the vacuum of space, as illustrated by quantum foam, challenges our understanding of reality and encourages deeper exploration into the fundamental workings of the universe. Quantum foam, a concept that arises from the field of quantum mechanics, refers to the idea that at the smallest scales of the universe, specifically at the Planck scale, the fabric of space-time is not smooth or continuous, but rather is composed of tiny, fluctuating bubbles, or foams. This phenomenon occurs at distances on the order of 10 to the power of 35 meters, which is unimaginably small, far beyond the reach of current experimental techniques, and even smaller than the size of subatomic particles like protons and electrons. At this scale, space-time is believed to be in constant flux, with particles popping in and out of existence, leading to a chaotic and dynamic structure that challenges our classical understanding of the universe. The concept of quantum foam was first proposed by physicist John Wheeler, who suggested that instead of viewing space-time as a smooth stage where events occur, we should think of it as a turbulent sea, where tiny fluctuations create a frothy appearance. These fluctuations are thought to be the result of the uncertainties inherent in quantum mechanics, where the very act of measuring a particle's position or momentum can alter its state, leading to a reality that is fundamentally probabilistic rather than deterministic. In this quantum landscape, the properties of particles, forces, and even gravity might behave in unexpected ways, potentially giving rise to phenomena that do not conform to our everyday experiences. For example, the implications of quantum foam stretch into theoretical physics, influencing ideas related to black holes, wormholes, and the nature of space-time itself. Some theorists propose that the structure of quantum foam could provide insights into the unification of general relativity and quantum mechanics, two pillars of modern physics that, despite their successes, remain largely incompatible at very small scales. As researchers delve deeper into the mysteries of quantum foam, they utilize advanced mathematical models and concepts from string theory and loop quantum gravity to explore how these tiny fluctuations could affect larger cosmic scales. For instance, if quantum foam does indeed influence the behavior of particles and forces, it might lead to a better understanding of dark matter and dark energy, which together account for a significant portion of the universe, yet remain elusive in terms of direct detection and understanding. Additionally, the study of quantum foam challenges our notions of time and space, suggesting that time itself may not be a continuous flow, but rather a series of discrete events, influenced by the underlying foamy structure of space-time. This idea invites us to rethink fundamental questions about the beginning. Quantum foam, a concept introduced by physicist John Wheeler, refers to the idea that at the smallest scales of space and time, the fabric of the universe is not smooth, but instead it is bubbling and frothy, constantly changing. At the Planck scale, which is about 10 to the power of 35 meters, quantum foam suggests that space-time is subject to extreme fluctuations, leading to an unpredictable environment for particles. This means that instead of behaving like solid, defined particles, entities at this scale could exhibit strange behaviors due to the turbulence of the foam. For instance, particles might not have a fixed position or momentum, as the very nature of space-time at this scale could cause them to appear and disappear or to shift between different states quite rapidly. The energy levels could also be affected, as the foam could create pockets of high or low energy, influencing how particles interact with one another. In this chaotic landscape, particles might find themselves in states of superposition, where they exist in multiple configurations simultaneously, much like the behavior observed in quantum mechanics at larger scales. Moreover, the fluctuations in quantum foam could lead to what is known as virtual particles, which are temporary particles that appear spontaneously and can influence the forces acting on real particles, further complicating their behavior. This phenomenon might illuminate some of the perplexing aspects of quantum entanglement, where particles appear to be connected in ways that defy classical physics, even when separated by vast distances. As researchers delve deeper into theories of quantum gravity, they are discovering that quantum foam might play a role in the unification of quantum mechanics and general relativity, possibly leading to new insights into black holes, the nature of dark energy, or even the very origin of the cosmos. The implications of quantum foam stretch beyond just the Planck scale, as they could provide a framework for understanding the early universe, where conditions were incredibly dense and chaotic, leading to the rapid expansion we call inflation. This bubbling nature of space-time challenges our perceptions and invites us to rethink our understanding of reality at its most fundamental level, fostering a sense of wonder and curiosity about the universe that surrounds us. Quantum foam, a concept born from the realm of quantum mechanics, refers to the idea that at the smallest scales of space and time, the very fabric of the universe is not smooth and continuous, but rather it is a frothy, turbulent sea of fluctuation. This idea, introduced by physicist John Wheeler, suggests that on the Planck scale, which is around 10 to the power of 35 meters, space-time is subject to constant fluctuations, creating a chaotic structure that resembles foam. This quantum foam is thought to be the foundation of reality, where virtual particles pop in and out of existence, influencing the behavior and properties of matter and energy. Now, when we consider black holes, those enigmatic regions in space where gravity is so strong that nothing, not even light, can escape, a fascinating relationship begins to emerge. As matter collapses under its own gravity to form a black hole, the intense gravitational forces at play are believed to interact with the quantum foam. The surface of a black hole, known as the event horizon, is thought to be where classical physics meets quantum mechanics. Here, the effects of quantum foam may play a crucial role in determining the information content of the black hole, which leads us to the famous black hole information paradox. This paradox arises from the conflict between quantum mechanics and general relativity, where information about the matter that falls into a black hole seems to be lost forever, violating the principles of quantum theory, which state that information cannot be destroyed. Some theorists speculate that the fluctuations of quantum foam could help resolve this paradox, suggesting that the information is not lost, but rather encoded in the quantum foam surrounding the black hole, or perhaps even on its event horizon, as proposed by the holographic principle. Moreover, the behavior of black holes might also provide insights into the nature of quantum foam itself. For instance, as black holes evaporate through Hawking radiation, a process that combines quantum mechanics with the gravitational effects of black holes, it raises questions about how quantum foam behaves in extreme gravitational environments. This interplay could lead to new understandings of both black hole physics and the fundamental structure of space-time. Additionally, as we explore the universe's most extreme phenomena, like the merging of black holes detected through gravitational waves, we might uncover further connections between quantum foam and black holes. These events, which produce ripples in space-time, could provide opportunities to study how quantum fluctuations manifest in the presence of powerful gravitational fields, potentially offering clues about the quantum nature of space. Constantly bubbling and fluctuating. This quantum foam suggests that space-time itself is subject to quantum effects, leading to a scenario where the very nature of reality is far more complex than our everyday experience might suggest. Now, when we bring string theory into the picture, we see intriguing intersections between these two concepts. String theory posits that the fundamental building blocks of the universe are not point-like particles, but rather tiny, vibrating strings, with different modes of vibration corresponding to different particles. In this framework, space-time is not just a backdrop, but a dynamic entity that interacts with these strings. Quantum foam plays a crucial role in string theory, particularly when we consider how space-time behaves at incredibly small scales, like at the Planck length, which is about 10 to the power of 35 meters. At this scale, traditional notions of space-time break down, and the fluctuations of quantum foam become significant. These fluctuations can impact the vibrations of strings, leading to a scenario where the properties of particles, such as mass and charge, may be influenced by the ever-changing geometry of space-time itself. Furthermore, some physicists theorize that the chaotic nature of quantum foam could give rise to the very dimensions beyond our familiar four, which string theory requires, as it typically posits the existence of additional spatial dimensions beyond the three we can easily perceive. As strings vibrate, they could interact with the quantum foam, perhaps giving rise to new physical phenomena or even affecting the formation of black holes and other cosmic structures. In this way, the intersection of quantum foam and string theory suggests a universe that is not only rich in complexity, but also deeply interconnected. The behavior at minuscule scales has profound implications for the larger cosmos. Researchers continue to explore these relationships, aiming to better understand how quantum fluctuations might influence everything from particle physics to the very structure of the universe itself, highlighting a landscape where the realms of quantum mechanics and gravitational theory. This ongoing exploration opens doors to new theories and ideas, potentially leading to a more unified understanding of the fundamental forces that govern everything we know. Quantum foam, a term coined by physicist John Wheeler, refers to the idea that on extremely small scales, space-time is not smooth and continuous as we often perceive it, but instead is made up of tiny, fluctuating bubbles or foam structures. This concept arises from the principles of quantum mechanics, where uncertainty and probabilistic events play a significant role. As we delve deeper into the fabric of the universe, at scales approaching the Planck length, which is about 1.6 times 10 to the power of 35 meters, the smooth, classical view of space-time breaks down, revealing a more chaotic and granular structure. The notion of quantum foam suggests that space-time, rather than being a continuous entity, is actually composed of discrete units, much like grains of sand on a beach. This idea aligns with the principles of quantum mechanics, where particles exhibit both wave-like and particle-like properties, leading to the conclusion that the fundamental building blocks of reality may not be continuous, but rather quantized. The fluctuations in quantum foam can be thought of as virtual particles popping in and out of existence, creating temporary distortions in space-time. These fluctuations imply that at very small scales, the geometry of space-time could be subject to rapid changes, further emphasizing its discrete nature. Moreover, quantum foam challenges our classical understanding of gravity. In general relativity, gravity is described as the curvature of a smooth space-time caused by mass. However, if space-time is indeed granular, the behavior of gravity at these small scales becomes complex and might not follow the traditional rules we associate with relativity. Some theories propose that these quantum fluctuations could be responsible for phenomena such as black hole entropy and the information paradox, suggesting that the very structure of space-time could hold the key to understanding deeper aspects of the universe. The idea of a granular space-time also opens up discussions about the nature of black holes, which are often thought of as points of infinite density where space-time itself breaks down. If space-time is indeed foamy, the singularities we associate with black holes may not exist in the way we thought, leading to new insights into how matter and energy interact at extreme gravitational fields. Some physicists even speculate that these fluctuations in quantum foam could provide a mechanism for phenomena like Hawking radiation, where black holes can emit radiation and potentially lose mass over time. Additionally, quantum foam has implications for the nature of time itself. If space-time is granular, then time may not flow continuously. Quantum foam, a concept proposed by physicist John Wheeler, suggests that at the tiniest scales of space and time, the fabric of the universe is not smooth, but rather it is a frothy, bubbling sea of energy fluctuation. This notion stems from quantum mechanics and the belief that space-time itself may be subject to quantum effects, leading to a turbulent structure at the Planck scale, which is about 10 to the power of 35 meters. To gather evidence for this intriguing idea, considered several promising experiments and observations, each aiming to probe the very foundation of space-time. One approach involves the study of high-energy cosmic rays, which are particles from space that travel close to the speed of light. When these particles collide with the atmosphere, they create showers of secondary particles, and examining the patterns of these showers can provide clues about the underlying structure of space-time. If quantum foam exists, it might cause fluctuations in the paths of these high-energy particles, leading to unexpected behaviors that could be detected by observatories on Earth. Additionally, researchers are investigating phenomena related to black holes, as these regions of intense gravity might amplify the effects of quantum foam. The Hawking radiation, predicted by Stephen Hawking, suggests that black holes can emit particles due to quantum effects near their event horizons. If quantum foam influences the nature of this radiation, studying the properties of black holes, especially those that are smaller and more volatile, could yield insights into the reality of quantum foam. Another avenue of exploration includes gravitational wave observations. When massive objects like neutron stars or black holes collide, they produce ripples in space-time known as gravitational waves. Instruments like LIGO and Virgo have already detected these waves, and as they continue to refine their sensitivity, they may be able to detect deviations from the predictions of general relativity, which could hint at the presence of quantum foam. If the fabric of space-time is indeed frothy, then gravitational waves might exhibit unusual characteristics that could serve as evidence. Moreover, experiments involving particle accelerators, such as the Large Hadron Collider, could potentially reveal signatures of quantum foam. When protons collide at extraordinarily high energies, the conditions might mimic those of the early universe, where quantum fluctuations were more prevalent. By analyzing the products of these collisions, physicists hope to find anomalies or unexpected behaviors that could indicate the presence of quantum structures at very small scales. Finally, researchers are also looking at cosmological observations, particularly the cosmic microwave background radiation, which is the quantum foam. A fascinating concept in quantum physics refers to the idea that at the smallest scales, space-time is not smooth and continuous. Rather, is filled with tiny fluctuations, bubbles and fluctuations, much like a frothy ocean. This idea was first proposed by physicist John Wheeler in the 1960s, and it suggests that on the Planck scale, which is incredibly tiny, the very fabric of space-time is constantly bubbling and shifting. Now, when we consider wormholes, which are hypothetical passages through space-time that could create shortcuts between distant points in the universe, the connection to quantum foam becomes intriguing. Wormholes, often depicted in science fiction, are solutions to Einstein's equations of general relativity, suggesting that if they exist, they could allow for faster-than-light travel or connect distant regions of space in ways we can hardly imagine. Theoretical physicists have speculated that the quantum foam at the Planck scale might provide the necessary conditions for such structures to form. If space-time is indeed frothy and unstable at these minuscule scales, then it raises the possibility that wormholes could emerge from these fluctuations, potentially allowing for the creation of temporary passages through space-time. Furthermore, some theories propose that these wormholes may not just be static structures, but could be dynamic, constantly being formed and annihilated due to the quantum fluctuations of the foam. This means that the existence of wormholes could be a natural consequence of the quantum nature of reality rather than merely a mathematical abstraction. However, it's essential to note that while these ideas are exciting, they remain highly speculative. Many physicists are still grappling with how to reconcile quantum mechanics with general relativity, and the concept of wormholes intertwined with quantum foam adds another layer of complexity to this already intricate puzzle. While there are mathematical models suggesting that wormholes could exist, and while the idea of quantum foam provides a tantalizing glimpse into the underlying structure of the universe, empirical evidence is lacking. This interplay between quantum foam and wormholes opens up numerous questions regarding the nature of gravity, the fabric of space-time, and the fundamental workings of our universe, all of which remain at the forefront of modern theoretical physics. Whether we will ever be able to observe such phenomena or harness the potential of wormholes remains an open question, and as our understanding of quantum gravity evolves, so too might our insights Relationship between quantum foam and the enigmatic nature of quantum foam, a concept introduced by physicist John Wheeler, represents the idea that at the smallest scales of space-time, the fabric of the universe is not smooth, but rather a turbulent, frothy sea of fluctuations. This strange and fascinating structure occurs at the Planck scale, which is incredibly tiny, about 10 to the power of 35 meters. Far beyond our everyday experience, visualizing quantum foam is quite challenging because it exists at a scale that is many orders of magnitude smaller than atoms and even subatomic particles. However, scientists and artists alike have attempted to represent this concept in various ways, using both theoretical models and artistic interpretations. In theoretical physics, one way to visualize quantum foam is through complex diagrams that illustrate fluctuations in energy in space-time. These diagrams often depict a chaotic, bubbling landscape where tiny bubbles of virtual particles pop in and out of existence. This representation helps convey the idea that space-time is not a static entity, but rather a dynamic, ever-changing one. Some physicists liken it to a frothy ocean, where waves and ripples represent the fluctuations occurring at the quantum level, with the foam being the result of these rapid changes. Artists, too, have taken inspiration from this concept, creating visual art that captures the essence of quantum foam. These artistic interpretations often use swirling patterns, vibrant colors, and abstract forms to evoke the complexity and mystery of the quantum world. Such artworks can help bridge the gap between the abstract nature of quantum physics and our more intuitive understanding of the universe, allowing viewers to engage with these ideas on a more emotional level. Moreover, computer simulations have emerged as a valuable tool for visualizing quantum foam. By using advanced algorithms, physicists can create models that depict how space-time might behave at the quantum level. These simulations can show how fluctuations in energy might create a foamy structure, helping to illustrate the idea that empty space is not truly empty, but filled with the frenetic activity of virtual particles. While these representations are not direct observations, they provide a glimpse into the complex behavior of the universe at its most fundamental level. Despite these efforts, it's essential to remember that any visualization of quantum foam is ultimately an approximation, a way for us to conceptualize something that is inherently difficult to grasp. The real nature of quantum foam is likely far more complex than any model can fully capture, reflecting the limitations of our current understanding of quantum mechanics and the nature of reality itself. As technology advances in our understanding, quantum foam, a concept rooted in quantum mechanics, suggests that at the smallest scales of space and time, the fabric of the universe is not smooth and continuous, but rather it is a frothy, chaotic sea of fluctuations. This idea, proposed by physicist John Wheeler in the 1960s, implies that space itself is subject to intense fluctuations, which can have profound implications for our understanding of gravity. Traditional theories of gravity, such as Einstein's general relativity, treat gravity as a force that acts over a smooth space-time continuum. But when we introduce quantum foam into the mix, we begin to see gravity in a different light. At the quantum level, gravity may not act uniformly. Instead, it could be influenced by the inherent uncertainty and instability of space-time itself. This means that at extremely small scales, gravity could behave unpredictably to phenomena that are not explained by classical physics. For instance, if space-time is indeed foamy, then the gravitational field may also exhibit fluctuations which could challenge our current understanding of gravitational waves and how they propagate through space-time. This could lead to new insights into the nature of black holes, as the event horizons of black holes might be affected by the quantum foam, potentially resulting in new effects that we have yet to observe. Moreover, the implications of quantum foam extend to the concept of space-time itself. If space-time is constantly bubbling and changing, it raises questions about the very nature of reality. Can we even define a clear point in space and time if everything is in a state of flux? This could lead to a reevaluation of gravity as not just a force, but as an interplay between the fabric of space-time and the energy contained within that foam. Such a perspective might suggest that gravity could emerge from deeper quantum processes rather than being a fundamental force in its own right. Additionally, some physicists speculate that quantum foam could be tied to the search for a unified theory of quantum gravity, which aims to reconcile general relativity with quantum mechanics. In this quest, understanding the role of quantum foam might provide crucial clues about how gravity operates at the quantum level and could potentially lead to groundbreaking discoveries in the field of theoretical physics. In summary, the implications of quantum foam on the nature of gravity could reshape our understanding of the universe, revealing a more complex and intricate relationship between gravity, space-time, and the fundamental forces that govern the cosmos. As scientists continue to explore these ideas, quantum foam, a concept from quantum mechanics, refers to the idea that space-time is not a smooth continuum, but rather is composed of tiny, fluctuating bubbles, or foams, at the Planck scale, which is roughly 10 to the power of 35 meters. This notion arises from the principles of quantum theory, where particles and energy can appear and disappear, creating a frothy, ever-changing landscape of space-time. The implications of quantum foam could significantly influence cosmological models of the universe, especially in our understanding of the early universe, black holes, and the fundamental nature of gravity. In the context of the early universe, quantum foam suggests that instead of a smooth beginning to the cosmos, there was a chaotic, dynamic state where fluctuations in energy and space-time could have led to the rapid expansion known as cosmic inflation. This inflationary period, a crucial element in many cosmological models, may have been shaped by the characteristics of quantum foam, potentially providing explanations for the uniformity observed in the cosmic microwave background radiation and the large-scale structure of the universe. If quantum foam can indeed affect the fabric of space-time, it could lead to variations in density, influencing how matter clumps together and evolves over time. Furthermore, when considering black holes, quantum foam introduces intriguing questions about what happens at the event horizon, the boundary beyond which nothing can escape. The interaction of quantum foam with the intense gravitational field of a black hole could lead to phenomena that challenge our current understanding of physics, including the possibility of information being preserved in some form which directly relates to the black hole information paradox. This paradox remains a significant topic of debate among physicists, as it touches on the fundamental principles of quantum mechanics and general relativity. Moreover, the influence of quantum foam could extend to the very nature of gravity itself. Traditional models view gravity as a force that acts over a distance. But if space-time is indeed foam-like, gravity might have additional properties that could alter the way we perceive it on cosmic scales. The fluctuation of quantum foam could lead to non-intuitive gravitational effects, possibly even affecting the expansion rate of the universe, which has been observed to be accelerating. Understanding how quantum foam interacts with gravitational forces could provide insights into dark energy, the mysterious component that is driving this acceleration. As researchers continue to explore the intersection of quantum mechanics and cosmology, the role of quantum foam could unveil new dimensions of understanding about the universe's structure and behavior. The challenge lies in creating Planck length, which measures around 1.6 x 10 to the power of 35 meters, is a fundamental unit in physics that plays a crucial role in our understanding of the universe. At its most microscopic level, it is derived from three fundamental constants: the speed of light, the gravitational constant, and Planck's constant. This tiny measurement is significant because it represents the scale at which classical ideas about gravity and space-time cease to be valid, giving way to the strange and often counterintuitive realm of quantum mechanics. In the context of quantum foam, the concept of Planck length becomes even more fascinating. Quantum foam, a term coined by physicist John Wheeler, describes the fluctuating, ever-changing nature of space-time at incredibly small scales. According to this idea, at distances on the order of the Planck length, space-time is not smooth and continuous as we perceive it in our everyday lives, but rather is filled with tiny, chaotic fluctuations. These fluctuations can be thought of as bubbles of space-time that pop in and out of existence, creating a kind of foam-like structure. The significance of Planck length in relation to quantum foam lies in the idea that it sets the boundary for our current understanding of physics. When we try to probe distances smaller than the Planck length, we encounter extreme gravitational effects, and the very fabric of space-time becomes a dynamic, unpredictable entity. This leads to the breakdown of our classical theories, such as general relativity, which describes gravity on larger scales, and quantum mechanics, which governs the behavior of particles at tiny scales. As researchers delved into this area, they explore concepts like string theory and loop quantum gravity, which attempt to reconcile the interactions of gravity with quantum mechanics, suggesting that at the Planck scale, the universe might be composed of one-dimensional strings or quantized loops of space-time. These theories imply that the fundamental building blocks of the universe may not be particles, as we traditionally think of them, but rather these more abstract constructs that only manifest at such minuscule scales. Thus, the Planck length serves as a kind of threshold, beyond which our current theories may no longer apply, urging scientists to rethink the very nature of reality. This leads to profound implications, not only for our understanding of quantum physics, but also for the fundamental nature of the universe itself, as it challenges us to consider what space and time mean when viewed through the lens of quantum foam. As we continue to investigate these realms, quantum fluctuations, which are the temporary changes in energy that occur in empty space, play a crucial role in the concept of quantum foam, a term used to describe the fundamental, ever-changing nature of space-time at the smallest scales. At the heart of quantum mechanics, these fluctuations arise due to the uncertainty principle, proposed by Werner Heisenberg, which states that the exact position and momentum of a particle cannot both be precisely determined at the same time. This inherent uncertainty means that even in what we think of as a vacuum, particles can spontaneously pop in and out of existence, creating a bubbling, frothy state of energy, often likened to the surface of a boiling pot of water. As we dive deeper into this idea, we find that quantum foam exists at the Planck scale, which is incredibly tiny, around 10 to the power of 35 meters. At this minuscule scale, the smooth fabric of space-time that we perceive at larger scales breaks down into a chaotic, dynamic structure, where the very geometry of space-time is constantly fluctuating. This leads to the idea that space-time itself is not a static background, but rather an active player in the universe's behavior. These fluctuations can create temporary wormholes, tiny tunnels connecting different points in space and time, although they are too small and fleeting to be detected directly. Furthermore, the concept of quantum foam connects to various theories in modern physics, including string theory and loop quantum gravity, which attempt to unify general relativity and quantum mechanics. In these frameworks, the quantum foam might provide insights into the nature of gravity at very small scales, suggesting that gravity itself could emerge from the intricate dance of quantum fluctuations. As researchers explore these ideas, they are delving into profound questions about the nature of reality, the universe, and what lies beyond our current understanding of physics. While the notion of quantum foam might sound abstract or even fantastical, it has significant implications for cosmology, particularly in the context of the Big Bang. Some theories propose that before the Big Bang, the universe existed in a state dominated by quantum foam, leading to the rapid expansion of space-time that we observe today. This connection invites us to consider how our universe emerged from this primordial chaos and how the rules governing quantum mechanics might have shaped the very fabric of reality. In summary, quantum fluctuations contribute significantly to the concept of quantum foam by illustrating how the universe operates at the smallest scales, revealing a reality that is far more complex and dynamic than quantum foam. A concept proposed by physicist John Wheeler refers to the idea that at the smallest scales, space-time is not smooth, but rather it is frothy and turbulent, filled with tiny fluctuations. This notion emerges from quantum mechanics, which suggests that at extremely small distances, such as those near the Planck length, space-time undergoes rapid changes, creating a sort of foam that could have profound implications for our understanding of the universe's origins. One of the most intriguing theoretical implications of quantum foam concerns the nature of time and space at the very beginning of the universe. If space-time is indeed fluctuating at such small scales, this might suggest that the traditional concepts of time and space, as we understand them, break down in the earliest moments, potentially leading to a very different kind of reality than we experience today. This perspective could affect how we think about the Big Bang itself. Instead of a singular beginning where the universe expands from a point, quantum foam might imply a more complex, tangled state of existence, where the universe emerges from a chaotic interplay of quantum fields. This could lead to new models that incorporate quantum gravity, attempting to unify general relativity and quantum mechanics. As such, the beginnings of the universe might not be a simple explosion from a single point, but rather a more intricate process shaped by the underlying quantum structure of space-time. Moreover, the idea of quantum foam raises questions about the nature of black holes and their formation. If space-time is fluctuating, then regions of extreme curvature and density, like black holes, could be influenced by these quantum fluctuations, potentially leading to new insights into what happens inside black holes and how information is preserved or lost. This ties into the ongoing debates in theoretical physics about the information paradox associated with black holes and how quantum mechanics reconciles with gravitational effects. Another implication relates to the possibility of multiple universes, or the multiverse theory. If space-time is not uniform, but rather filled with quantum foam, it might allow for various configurations of space-time to exist simultaneously, leading to the idea that our universe is just one of many, each with its own unique properties and laws of physics. This could radically change our understanding of existence itself, suggesting that our universe is just a tiny bubble within a vast sea of other potential universes, each with its own distinct characteristics, emerging from the same underlying quantum structure. In addition, quantum foam might help explain some of the mysteries surrounding dark energy and dark matter, as This notion ties closely to the inflationary model of the universe, which suggests that shortly after the Big Bang, the universe underwent an exponential expansion, stretching space-time rapidly and smoothing out any irregularities. Quantum foam can be thought of as the microscale fluctuations that existed in the early universe. Before inflation took hold, creating a turbulent environment where the fabric of space-time was highly dynamic. As the universe expanded, these tiny fluctuations in quantum foam could have been stretched to macroscopic scales, influencing the distribution of matter and energy throughout the universe. In this way, quantum foam may have played a role in seeding the large-scale structures we see today, such as galaxies and clusters of galaxies. The inflationary model posits that these quantum fluctuations, which arose from the uncertainty principle of quantum mechanics, were stretched during the rapid expansion, imprinting tiny variations in density that later evolved into the stars and galaxies we observe across vast cosmic distances. Moreover, the energy associated with quantum fluctuations might have contributed to the inflationary process itself. Some theories suggest that a scalar field, known as the inflaton field, drove this rapid expansion, and the energy of this field could have interacted with the quantum foam, further influencing the dynamics of the early universe. The interplay between quantum mechanics and general relativity, particularly in the context of an inflationary universe, raises profound questions about the nature of reality, the fabric of space-time, and the very origins of the universe. In addition, the relationship between quantum foam and inflation touches upon the quest to unify quantum mechanics and general relativity, a goal that has eluded physicists for decades. Understanding how these quantum fluctuations can lead to the large-scale structure of the universe could provide insights into the fundamental workings of the cosmos, revealing how the laws of physics operate at both the smallest and largest scales. Thus, the concept of quantum foam not only enhances our understanding of the inflationary model, but also invites us to ponder the deeper connections between the quantum realm and the vast universe we inhabit. Quantum foam, a term coined by physicist John Wheeler, refers to the idea that at the smallest scales of space and time, the fabric of the universe is not smooth, but rather, it is constantly fluctuating and bubbling with activity. This concept emerges from the framework of quantum mechanics and combines with the principles of general relativity to address some of the most profound questions in theoretical physics, particularly in the quest to understand quantum gravity. In essence, quantum foam suggests that space-time is not a uniform entity, but instead it is a dynamic and chaotic environment filled with fleeting virtual particles and energy fluctuations, which could have implications for how gravity operates at the quantum level. In the context of quantum gravity, the role of quantum foam becomes significant when we consider how gravity, which is traditionally described by Einstein's general relativity as a curvature of space-time, interacts with the principles of quantum mechanics, which govern the behavior of particles at the smallest scales. Quantum foam might provide insights into how space-time itself is quantized, leading to the idea that at extremely small scales, like the Planck length, the smooth structure of space-time breaks down, and instead, a frothy, ever-changing landscape emerges. I tell you, this notion aligns with various approaches to quantum gravity, including loop quantum gravity and string theory, both of which attempt to reconcile the differences between quantum mechanics and general relativity. The fluctuations represented by quantum foam could potentially lead to phenomena that challenge our conventional understanding of gravity. For example, as particles pop in and out of existence in this foamy background, they could influence the gravitational interactions between larger objects. Some theorists propose that these minute fluctuations might even give rise to a form of gravitational waves, not unlike those detected from distant cosmic events, albeit on scales that are currently beyond our technological reach to observe directly. Moreover, quantum foam raises intriguing questions about the nature of black holes and the information paradox, as the highly energetic environment near a black hole's event horizon could be affected by these quantum fluctuations. This interplay might provide new insights into how information is preserved or lost in the universe, a topic that has perplexed physicists since the early days of quantum mechanics. In summary, while quantum foam is still a theoretical construct, its implications for our understanding of quantum gravity are profound. offering a glimpse into a universe that is more complex and dynamic than we could ever have imagined, challenging the boundaries of our knowledge and inviting further exploration into the fundamental nature of reality. Quantum foam, a term popularized by physicist John Wheeler, refers to the idea that at the smallest scales of the universe, space-time is not smooth and continuous, but rather it is a frothy, chaotic, and ever-changing structure. This concept arises from quantum mechanics, where particles and energy are not static but are instead in a constant state of fluctuation. At incredibly small scales, on the order of the Planck length, which is about 1.6 times 10 to the power of 35 meters, space-time is thought to be subject to quantum uncertainties, creating a kind of foam of virtual particles popping in and out of existence. This idea fundamentally challenges our classical understanding of time, which we often perceive as a steady flowing river. As we delve into the implications of quantum foam, we start to realize that time, at these minuscule scales, may not behave in the linear fashion we are accustomed to. Instead, time could be seen as being influenced by the fluctuations in this quantum foam. For instance, if space-time is constantly fluctuating, it raises questions about the nature of causality and the very fabric of reality. How do events unfold if the underlying structure of space-time is not stable? This notion may suggest that time could be more granular or quantized at such small scales, where intervals of time could have a minimum size, similar to how energy levels in atoms are quantized. Moreover, the concept of quantum foam can also lead us to rethink the relationship between time and gravity. In Einstein's theory of general relativity, gravity is a curvature of space-time caused by mass. However, if space-time itself is constantly bubbling with quantum activity, then the very nature of gravity could be influenced by these fluctuations. This means that the flow of time could also be affected. Areas of space that experience different densities of quantum foam might have different rates of time passage. This could potentially align with some interpretations of the effects of strong gravitational fields, such as those near black holes, where time appears to slow down relative to observers further away. Furthermore, the implications of quantum foam extend into the realm of theoretical physics and cosmology. If space-time is indeed foamy, it could have consequences for our understanding of the early universe, immediately after the Big Bang, when the universe was incredibly small and dense. During this epoch, conventional laws of time and space may not apply, leading to new models of cosmic evolution that incorporate the effects of quantum foam. A term introduced by physicist John Wheeler refers to the idea that at the smallest scales, space-time is not smooth, as we often think of it, but instead is a frothy, turbulent sea of fluctuation. This concept emerges from the principles of quantum mechanics, suggesting that on extremely tiny scales, such as the Planck scale, space-time is subject to quantum effects that create a chaotic and dynamic structure. On the other hand, general relativity, formulated by Albert Einstein, describes gravity as the curvature of a smooth, continuous fabric of space-time, which is influenced by mass and energy. This poses an intriguing challenge, as reconciling these two frameworks, quantum mechanics and general relativity, is one of the biggest puzzles in modern physics. To bridge this gap, some physicists propose that quantum foam and the smooth nature of space-time can coexist, albeit in a more complex relationship than we currently understand. One approach is to consider that while space-time appears smooth at larger scales, this smoothness could emerge from the underlying quantum fluctuation. In this view, the quantum foam operates like the ripples on the surface of a pond. From a distance, the water seems calm and uniform, but up close, the chaotic movement of individual water molecules becomes apparent. This idea suggests that the smooth fabric of space-time is an effective theory emerging from the underlying quantum behavior. Additionally, theories such as loop quantum gravity attempt to describe the fabric of space-time itself as being composed of discrete units or a quanta, rather than being a continuous medium. This aligns with the notion of quantum foam, suggesting that at the smallest scale, space-time is granular. In such a framework, quantum foam could be thought of as the fundamental structure from which smooth space-time emerges at larger scales. This is a significant departure from traditional views. Moreover, string theory, another candidate for unifying quantum mechanics and general relativity, posits that the fundamental building blocks of the universe are not point particles, but rather tiny vibrating strings. These strings could exist in multiple dimensions, further complicating our understanding of space-time. In string theory, the interactions and vibrations of these strings could give rise to the smooth geometry of space-time, while still allowing for the quantum fluctuations that quantum foam represents. As scientists continue to explore these ideas, experimental evidence, such as the concept of quantum foam, which arises from the field of quantum mechanics, presents a fascinating intersection of physics and philosophy, leading to numerous implications regarding the nature of reality itself, the fabric of space-time, and our understanding of existence. Quantum foam, as proposed by physicist John Wheeler, suggests that at the tiniest scales, space-time is not smooth and continuous, but rather it is turbulent and frothy, filled with fluctuations and virtual particles popping into and out of existence. This idea challenges our traditional perceptions of a fixed, unchanging universe, and introduces a level of uncertainty and dynamism that can be startling. One of the philosophical implications is the question of determinism versus indeterminism. If quantum foam implies that events at the quantum level can be fundamentally unpredictable, then what does that mean for our understanding of causality? If the universe operates on a level where uncertainty reigns, it forces a reconsideration of free will, and whether our choices are truly our own, or if they are influenced by a vast, chaotic web of quantum events. Moreover, the notion of quantum foam also has implications for the nature of reality itself. If reality is composed of these minute fluctuations, it raises questions about the solidity of the objects we perceive around us, or what we see and interact with, mere manifestations of deeper, fluctuating quantum processes. This can lead to a philosophical inquiry into the nature of existence. What does it mean to exist if the very basis of our universe is in constant flux? Furthermore, this can spark discussions about the nature of time, as the persistent fabric of time may also be subject to these quantum fluctuations, blurring the lines between past, present, and future. Additionally, the implications extend to the fields of metaphysics and ontology, as the quantum foam concept suggests that our understanding of space-time may be incomplete. If space-time is fundamentally granular rather than continuous, it may challenge the very way we think about the universe, leading to a reevaluation of how we define objects, entities, and even the concept of emptiness. This could mean that our traditional views on the separation of objects in space may need to be revisited, as the boundaries between them might not be as clear-cut as we once believed. Moreover, the existence of quantum foam can also lead to ethical and existential questions. If reality is a complex interplay of quantum events, what does it mean for our responsibilities? With the understanding that everything is interconnected at a fundamental level. Quantum foam, a concept rooted in the realm of quantum mechanics, introduces intriguing possibilities for our understanding of causality in physics. This idea, proposed by physicist John Wheeler, suggests that the smallest scales of space-time, the fabric of the universe, is not smooth, but rather it is composed of tiny, ever-fluctuating bubbles, or foams. These fluctuations occur at the Planck scale, which is about 10 to the power of 35 meters, a distance so minuscule that it challenges our traditional notions of space and time. As we delve into the implications of quantum foam, we begin to see how it might alter our perception of cause and effect. In classical physics, causality implies a clear, linear relationship where one event leads to another in a predictable manner. When we consider the chaotic nature of quantum foam, this linearity becomes less certain. The random, dynamic changes in this foam could lead to situations where events are not strictly causative, but rather interconnected in complex and non-linear ways. For example, if the very structure of space-time is in constant flux, then the concept of a singular cause leading to a singular effect might be too simplistic. Instead, multiple events could occur simultaneously, influencing each other in ways that are not easily traceable. This brings us to the idea of retrocausality, which suggests that future events could influence past ones, a notion that feels counterintuitive but gains traction in light of quantum foam. If the fabric of reality is continuously shifting, then the sequence of events might not be as fixed as we once thought, allowing for a different interpretation of time itself. Researchers are exploring how these fluctuations could lead to scenarios where causation is bidirectional, meaning that what we perceive as a cause might actually be influenced by effects that haven't yet occurred. Furthermore, quantum foam challenges our understanding of determinism, which is the philosophical idea that every event is determined by preceding events and natural laws. If the structure of space-time is inherently unpredictable due to quantum fluctuations, it raises questions about whether our universe is deterministic or fundamentally probabilistic. This uncertainty could mean that while we can model and predict certain outcomes, the underlying reality is much more fluid and subject to change than we can observe. In addition, the implications of quantum foam extend to our understanding of black holes and the information paradox. When we consider how particles behave at the quantum level near the event horizon of a black hole, the idea of quantum foam, which is the idea that space-time is not smooth but rather fluctuates at extremely small scales, could lead to a variety of exciting technological applications. One potential application is in the field of quantum computing. By grasping the underlying principles of quantum foam, scientists may be able to develop more robust quantum systems, allowing for the creation of quantum computers that are less susceptible to noise and interference, thus enhancing their computational power and efficiency. This could revolutionize fields such as cryptography, materials science, and complex system modeling, as quantum computers could solve problems that are currently intractable for classical computers. Another area where quantum foam might have a significant impact is in the development of advanced sensors. Understanding the fluctuations of space-time at a quantum level could lead to the design of ultra-sensitive detectors that could measure gravitational waves or other minute changes in the fabric of space-time, which could have applications in astrophysics and fundamental physics research. These sensors could also be used in various industries, from navigation systems to medical imaging, offering new ways to detect and analyze tiny changes in physical systems. Additionally, quantum foam may open doors to innovations in energy storage and transmission. By leveraging the principles of quantum mechanics, researchers could develop new materials that harness the fluctuations of quantum foam for efficient energy transfer, potentially leading to breakthroughs in battery technology or even new forms of energy generation. Imagine batteries that charge in seconds, or energy systems that lose minimal power during transmission, thanks to insights gained from quantum foam research. Moreover, there are implications for our understanding of gravity and its role in the universe. If researchers can manipulate or understand quantum foam, this might lead to technologies that can create or control gravitational fields. Such advancements could transform transportation systems, enabling new modes of travel that are currently only found in science fiction, like gravity-based propulsion systems that could revolutionize air and space travel. In the realm of materials science, the insights gained from studying quantum foam could inspire the development of new materials with unique properties. For instance, materials that mimic the behavior of quantum foam could exhibit extraordinary strength, flexibility, or conductivity, leading to advancements in everything from construction to electronics. Nanotechnology could benefit from these discoveries as well, with the potential to create nanoscale devices that operate on fundamentally different principles, leading to new applications in medicine, computing, and engineering. Finally, the philosophical and theoretical implications of quantum foam could inspire new ways of thinking about reality and our place in the universe. As we deepen our understanding of space-time, scientists theorize about the interaction between quantum foam and dark matter by delving into the realms of quantum physics and cosmology, where these two concepts, seemingly disparate, might reveal deeper connections within the universe. Quantum foam, a term popularized by physicist John Wheeler, refers to the idea that at the smaller scales of space-time, the fabric of the universe is not smooth, but rather is filled with tiny fluctuations, bubbling up and down as if it were a frothy sea of energy and particles. This concept suggests that space-time itself is dynamic, with particles constantly appearing and disappearing, creating a kind of turbulent environment at the quantum level. Meanwhile, dark matter, which makes up about 27% of the universe, is a mysterious substance that does not emit, absorb, or reflect light, and its presence is inferred from gravitational effects on visible matter, radiation, and the large-scale structure of the universe. To explore the interaction between these two phenomena, scientists often use theoretical frameworks that incorporate aspects of quantum field theory and general relativity. One idea is that the fluctuations in quantum foam could give rise to virtual particles, which might interact with dark matter particles. This interaction could potentially influence the properties of dark matter, such as its distribution and behavior in galaxies. Some researchers propose that if dark matter particles are indeed influenced by the dynamic nature of quantum foam, they may exhibit effects that could be detectable in high-energy cosmic events, such as gamma-ray bursts or through gravitational wave observations. In addition to that, there are theories suggesting that dark matter could be made up of particles that are very light and interact with the quantum foam in a unique way. This means that dark matter might not be as stable as previously thought, and its properties could change depending on the fluctuations of the quantum foam. This perspective opens up fascinating avenues for research, as scientists can look for signs of these interactions through astrophysical observations and experiments designed to detect dark matter particles. Moreover, some theoretical physicists are investigating the possibility that quantum foam might play a role in the formation of dark matter halos around galaxies. If the fabric of space-time is indeed bubbling with energy at the quantum level, it could influence the gravitational fields that hold dark matter, potentially leading to new insights about the structure of the universe. This interplay between the micro world of quantum mechanics and the macro world of cosmic structures is a thrilling area of study, as it challenges our understanding of fundamental physics. As scientists continue to explore these theories, they rely on quantum foam, a concept rooted in the realm of quantum mechanics, suggests that at the smallest scale, space-time is not smooth and continuous, but rather is composed of tiny fluctuating bubbles, or foam. This idea, introduced by physicist John Wheeler, implies that the very fabric of the universe is dynamic, constantly changing, and filled with ephemeral particles that pop in and out of existence. One of the intriguing implications of quantum foam is its potential relationship with phenomena like Hawking radiation, which was proposed by physicist Stephen Hawking in 1974. Hawking radiation arises near the event horizon of a black hole, where the intense gravitational field leads to the creation of particle-antiparticle pairs. Normally, these pairs annihilate each other almost instantly, but in the extreme environment near a black hole, one particle can fall into the black hole while the other escapes, resulting in a form of radiation that can be detected from outside the black hole. Now, if we consider quantum foam, it can be envisioned as providing the underlying structure that allows this particle-antiparticle creation to occur. The fluctuations in quantum foam could facilitate the energy necessary for these pairs to materialize, thus contributing to the conditions that lead to Hawking radiation. In this context, quantum foam operates at a scale where the effects of gravity and quantum mechanics intertwine, highlighting the importance of understanding how space-time behaves at the Planck scale. As such, the chaotic nature of quantum foam might give rise to unpredictable fluctuations in energy density, which could support the emergence of virtual particles. Moreover, the interactions between the quantum foam and the strong gravitational fields of black holes could enhance the production of these particles, making it more likely for them to escape rather than annihilate each other. This could mean that quantum foam plays a significant role in the very mechanism of Hawking radiation, where the randomness of the foam might lead to a greater likelihood of particle pairs being created just outside the event horizon, allowing one of the particles to become real, escaping the black hole's grasp. Additionally, understanding the relationship between quantum foam and Hawking radiation might provide insights into the nature of black holes themselves. This is particularly relevant in the study of black hole thermodynamics, which explores how black holes can emit radiation and eventually evaporate over time. The concept of quantum foam could help bridge the gap between general relativity and quantum mechanics, two pillars of modern physics that often seem incompatible, suggesting a deeper, unified theory of gravity. That the study of quantum foam, a concept rooted in quantum gravity, presents intriguing connections to the burgeoning field of quantum computing. Quantum foam refers to the idea that at the smallest scales, the fabric of space-time is not smooth, but instead is a frothy, turbulent structure, filled with tiny fluctuations and virtual particles popping in and out of existence. This phenomenon is thought to occur at the Planck scale, which is around 10 to the power of 35 meters, and it suggests that space-time may be more dynamic and complex than previously understood. In the realm of quantum computing, this understanding of space-time could influence how we think about qubits, the basic units of quantum information. Unlike classical bits that can be either a 0 or a 1, qubits can exist in superpositions of states, allowing for far more complex computations. The behavior of qubits is governed by the principles of quantum mechanics, which are also influenced by the fabric of space-time, and therefore the concepts of quantum foam could shed light on how qubits interact with each other and their environment. As quantum computing relies on phenomena such as entanglement and superposition, the dynamic nature of quantum foam could play a crucial role in the development of more robust quantum systems. For instance, understanding how these fluctuations in space-time might affect qubit coherence and error rates can lead researchers to design better quantum error correction methods. Since quantum computers are sensitive to their surroundings, the insights gained from studying quantum foam could help mitigate the effects of decoherence, a major challenge in the field. Furthermore, the exploration of quantum foam aligns with the concept of quantum field theory, which underpins much of modern physics, and as quantum computing continues to evolve, it may benefit from the principles and mathematical frameworks that arise from the study of quantum gravity and space-time dynamics. Additionally, researchers are investigating whether the principles of quantum foam could inspire new algorithms or computational models that leverage the inherent uncertainty found at the quantum level. By understanding the fluctuations and irregularities of quantum foam, scientists might develop quantum algorithms that exploit these features for improved computational efficiency. Moreover, as scientists probe deeper into the nature of space-time and its quantum properties, this research could lead to breakthroughs in quantum hardware, enhancing the stability and connectivity of quantum systems, which are critical for developing practical quantum computers. The intersection of quantum foam and quantum computing thus represents a fascinating frontier, where fundamental physics meets cutting-edge technology, potentially leading to revolutionary advancements in how we process information and understand the universe. Observing quantum foam, a concept rooted in quantum gravity, presents a series of intricate challenges that scientists are still grappling with. Quantum foam, which theorizes that at the Planck scale, space-time is not smooth but rather fluctuates wildly, is difficult to observe directly because it operates at scales so tiny that our current technology is not equipped to measure them effectively. The Planck scale, where quantum foam is theorized to exist, is around 10 to the power of 35 meters, which is many orders of magnitude smaller than the particles we can currently detect. This means that to experimentally observe quantum foam, we would need instruments that can reach unprecedented levels of sensitivity and resolution, far beyond what is currently available. Moreover, the effects of quantum foam are expected to be incredibly subtle, blending in with the noise of other quantum phenomena. Distinguishing the signature of quantum foam from other quantum fluctuations poses a significant challenge, as the signals we might expect to see could easily be drowned out by the myriad of other interactions happening at the quantum level. This requires not only advanced technology, but also innovative methods of data analysis to sift through the noise and pinpoint the faint signals that could indicate the presence of quantum foam. Another considerable challenge lies in the theoretical framework itself. Quantum foam arises from the interplay of quantum mechanics and general relativity, two pillars of modern physics that have yet to be reconciled into a single, unified theory. This lack of a comprehensive theory makes it difficult to predict exactly what we should be looking for when searching for evidence of quantum foam. Without clear theoretical predictions, designing experiments becomes more of a shot in the dark, rather than a guided quest for specific phenomena. Additionally, the extreme energies required to probe the Planck scale are beyond our current experimental capabilities. For instance, particle colliders like the Large Hadron Collider, which is currently the most powerful collider in existence, operates at energies far too low to access the Planck scale. To experimentally observe quantum foam, we would need to achieve energy levels that could create conditions similar to those present in the very early universe, moments after the Big Bang. This poses logistical, financial, and technological hurdles that can be daunting to overcome given the current state of our experimental facilities. Furthermore, any potential observations of quantum foam must contend with the uncertainty principle, a fundamental concept in quantum mechanics that limits our ability to measure certain pairs of properties simultaneously. This principle implies that the act of observing quantum foam itself could influence its state, making quantum foam, a concept introduced by physicist John Wheeler, represents the idea that at the smallest scales of space and time, the fabric of the universe is not smooth and continuous, but rather turbulent and frothy, with tiny fluctuations occurring constantly. This phenomenon occurs at the Planck scale, which is roughly 10 to the power of 35 meters, where classical ideas of gravity and space-time break down. Understanding quantum foam is crucial, as it helps bridge the gap between quantum mechanics and general relativity, providing insights into how entangled particles interact over vast distances. Entanglement, a fundamental aspect of quantum mechanics, describes a situation where two particles become linked in such a way that the state of one particle instantly influences the state of the other, regardless of the distance separating them. The relationship between quantum foam and entanglement can be seen in the way that quantum fluctuations might contribute to the non-local connections that define entangled systems. When particles are entangled, they share information instantaneously, which seems to challenge our traditional understanding of space and time. The presence of quantum foam suggests that space-time itself might be more dynamic than previously thought, implying that these fluctuations could facilitate or even be the source of the instantaneous interactions observed in entangled particles. Moreover, the concept of quantum foam raises intriguing questions about the nature of reality, as it suggests that the universe is a complex, ever-changing tapestry of probabilities. This idea encourages scientists to explore how entanglement might be influenced by the underlying structure of space-time, potentially leading to new theories that reconcile quantum mechanics with the principles of relativity. Some researchers speculate that the connections between entangled particles could be mediated by these quantum fluctuations, making them a crucial aspect of understanding how information is transferred in the quantum realm. In recent years, advances in quantum computing and quantum information theory have led to practical applications of entanglement, but the implications of quantum foam remain largely theoretical. Nevertheless, physicists are studying the links between these concepts, hoping to uncover deeper truths about the universe. As experiments continue to probe the nature of entanglement, researchers are also investigating how space-time might behave at extremely small scales, where quantum foam is at play, to gain a fuller understanding of the fundamental forces governing our universe. This exploration is not just an academic exercise, it has the potential to revolutionize our understanding of the cosmos. By examining the interplay between quantum foam and entanglement, scientists aim to unlock new perspectives on the very foundations of reality, offering the concept of quantum foam, which was proposed by physicist John Wheeler, suggests that at the smallest scales of space and time, the fabric of the universe is frothy, bubbling, and constantly in flux, essentially made up of tiny, ever-changing fluctuations in energy. While this idea has captured the imagination of many, there are several critiques and alternative theories that challenge or expand upon the concept of quantum foam. Some physicists argue that quantum foam might not accurately represent the nature of space-time at the Planck scale, suggesting instead that space-time could be smooth rather than frothy at these incredibly small scales. This perspective is supported by certain interpretations of string theory, which propose that fundamental particles are not point-like, as quantum foam would imply, but rather one-dimensional strings vibrating at specific frequencies, leading to a more continuous structure of space-time. Another alternative is the idea of loop quantum gravity, which attempts to reconcile general relativity with quantum mechanics. In this framework, space-time itself is quantized, composed of discrete loops. This theory suggests that, instead of a chaotic foam, space-time possesses a more structured, network-like quality, which may provide a clearer picture of how gravity operates at the quantum level. Critics of quantum foam also point out that the concept raises questions about how such fluctuations would manifest in observable phenomena. For instance, if space-time is indeed constantly bubbling, one might expect to observe significant effects on the behavior of particles and light, but so far, experiments have not definitively confirmed these predictions. Furthermore, some theorists propose that the fabric of the universe might be better understood through the lens of holographic principles, where all the information contained within a volume of space can be represented as a two-dimensional surface. This challenges the need for a concept like quantum foam because, in a holographic universe, the apparent three-dimensional nature of reality could emerge from deeper, underlying processes that do not require the frothy picture that quantum foam presents. Additionally, it's important to consider the philosophical implications of quantum foam and similar theories, as they often touch on fundamental questions about reality, observation, and the limits of human understanding. Many scientists and philosophers debate whether the nature of reality at such small scales can ever truly be known, given the limitations of current experimental techniques and the inherent uncertainties of quantum mechanics. As research in theoretical physics continues to evolve, alternative theories and critiques of quantum foam encourage a broader exploration of the fundamental nature of reality, pushing the boundaries of what we know. Future advancements in technology stand to significantly enhance our study of quantum foam, which is a concept derived from quantum mechanics, suggesting that at the smallest scales, space and time are not smooth, but rather are composed of tiny, fluctuating bubbles, or foam. To delve into this elusive realm, we might first leverage the power of quantum computing, which, with its ability to perform complex calculations at unprecedented speeds, could enable us to simulate quantum foam more effectively than traditional computers. By harnessing qubits, which can exist in multiple states simultaneously, researchers could model the interactions within quantum foam, offering insights into how these tiny fluctuations might influence the fabric of space-time itself. Moreover, advancements in high-energy particle physics could play a crucial role in enhancing our understanding of quantum foam. The construction of more powerful particle accelerators, such as the proposed future circular collider, could allow us to probe deeper into the fundamental forces of nature. By smashing particles together at energies never before achieved, we might create conditions that reveal the properties of quantum foam, shedding light on how it behaves under extreme circumstances, which could lead to groundbreaking discoveries regarding gravity, dark matter, and the origins of the universe. Additionally, breakthroughs in observational technology, particularly in the field of astrophysics, could offer new avenues to study quantum foam indirectly. For example, the development of more sensitive gravitational wave detectors could help us observe phenomena that may be influenced by the structure of space-time at quantum levels. By analyzing gravitational waves from distant cosmic events, we could gather evidence supporting or challenging existing theories about the nature of quantum foam, thus enhancing our overall understanding of the universe. Nanotechnology, too, could contribute significantly to our research into quantum foam. The ability to manipulate materials at the nanoscale may enable scientists to create devices that can probe the properties of space-time in ways previously thought impossible. For instance, nanoscale sensors could potentially detect the minuscule fluctuations in energy that quantum foam entails, providing empirical data that could confirm theoretical predictions. Furthermore, artificial intelligence and machine learning can assist researchers in analyzing vast amounts of data generated by experiments related to quantum mechanics. By employing advanced algorithms, we can identify patterns and correlations within the data that might indicate the behavior of quantum foam, thus accelerating the pace of discovery in this fascinating field. In summary, the future of studying quantum foam is likely to be shaped by a confluence of technological advancements across various disciplines, each contributing unique insights and tools. As we continue to push the boundaries of our understanding of the concept of quantum foam, which comes from quantum mechanics, suggests that at the smallest scales of space and time, the fabric of the universe is not smooth, but rather it is turbulent and frothy, filled with tiny fluctuations. This idea, originally proposed by physicist John Wheeler in the 1950s, implies that at the Planck scale, which is about 10 to the power of 35 meters, space-time itself is subject to constant, rapid changes resembling a chaotic sea of virtual particles popping in and out of existence. This chaotic, fluctuating nature of space-time raises fascinating questions about the structure of reality and leads us to the intriguing idea of the multiverse, which posits that our universe is just one of many potentially infinite universes that exist simultaneously. The relationship between quantum foam and the multiverse can be understood through various theoretical frameworks, such as string theory and cosmic inflation. In string theory, which attempts to unify quantum mechanics with general relativity, the idea of quantum foam suggests that the different vibrational modes of strings could correspond to different particles, and by extension, different universes. Each universe could have its own unique properties, and the fluctuations of quantum foam could allow for the emergence of entirely new universes through mechanisms like bubble nucleation. This process happens when a region of space undergoes a phase transition, leading to a new universe forming in a higher energy state, separate from our own. In this view, the quantum foam serves as the underlying fabric from which these bubbles of universes could emerge, each with its own distinct physical laws and constants. Additionally, in the context of cosmic inflation, which is a theory that explains the rapid expansion of the universe shortly after the Big Bang, Quantum foam plays a crucial role. During inflation, quantum fluctuations can be amplified, leading to regions of space that expand at different rates, potentially creating isolated pocket or bubble universes. These bubbles can have varying characteristics, such as different dimensionalities or fundamental forces, leading to a vast multiverse where each universe has its own unique set of rules. The connection between quantum foam and inflation exemplifies how the unpredictable nature of the quantum realm can give rise to a rich variety of cosmic landscapes, further supporting the multiverse hypothesis. Moreover, the implications of quantum foam extend into theories of dark energy and cosmic structure. The fluctuations in quantum foam might offer insights into the distribution of dark matter and dark energy, which are fundamental to understanding the universe's expansion. Quantum foam, a term coined by physicist John Wheeler, refers to the idea that at the smallest scales, space-time is not smooth, but rather is filled with tiny, fluctuating bubbles of energy, which exist at the Planck scale, that's around 10 to the power of 35 meters. This concept suggests that on these incredibly small scales, space-time is dynamic and constantly changing, leading to a foamy texture. This notion of quantum foam relates intriguingly to space-time singularities, which are points in the universe where the gravitational field becomes infinite, such as at the center of black holes or during the Big Bang. Singularities represent a breakdown of our understanding of physics, where current theories cannot adequately describe what happens, and it is at these points that the effects of both quantum mechanics and general relativity become crucial. As quantum foam suggests that space-time itself is subject to quantum fluctuations, this raises fascinating questions about the nature of singularities. For instance, if space-time is indeed foamy at the quantum level, then singularities may not be as absolute as once thought. Instead, they could be regions where the effects of quantum mechanics play a significant role, potentially leading to new physics that could resolve the contradictions between general relativity and quantum mechanics. This interplay suggests that rather than being rigid, the behavior of space-time might be influenced by quantum effects, which could prevent the formation of singularities in the traditional sense. Moreover, some physicists propose that instead of singularities, we might encounter where the foamy nature of space-time allows for the smooth transition of matter and energy, avoiding the infinite densities that singularities would imply. This idea connects back to theories like loop quantum gravity, which attempts to reconcile general relativity and quantum mechanics, suggesting that space-time has a discrete structure made of tiny loops. In such a framework, the quantum foam could lead to a modified understanding of black holes, possibly preventing the formation of singularities altogether, as the energy density might not reach infinity within the structure of space-time. Additionally, studying quantum foam could provide insights into the very early universe, right after the Big Bang, where space-time was likely dominated by quantum fluctuations. In this scenario, the chaotic nature of quantum foam could have influenced the expansion of the universe, leading to the large-scale structure we observe today. The connection between quantum foam and singularities challenges our understanding of fundamental physics and indicates that we may need to rethink our quantum foam. A concept emerging from the realm of quantum gravity represents the idea that at the smallest scales, space-time is not smooth and continuous, but rather is filled with constant fluctuations and chaotic activity. Akin to a bubbling foam, this phenomenon occurs at the Planck scale, which is about 10 to the power of 35 meters, far smaller than anything we can currently observe directly. In this frothy realm, virtual particles come in and out of existence, and space-time itself exhibits a kind of dynamic instability. When discussing how quantum foam interacts with fundamental forces such as electromagnetism, we venture into a complex and fascinating area of theoretical physics, where our current understanding is still being developed. Electromagnetism, one of the four fundamental forces of nature, governs how charged particles interact with each other through electric and magnetic fields. The exchange of photons, which are the force carriers of electromagnetism, happens on a scale that typically involves larger structures than those described by quantum foam. However, when we consider the implications of quantum foam, the interactions of particles can become influenced by the fluctuations in space-time itself. In essence, the foam acts as a backdrop for these electromagnetic interactions, where the very fabric of space-time can influence the behavior of particles and fields. In regions of high-energy physics, such as near black holes or during the early moments of the universe, the effects of quantum foam might become significant. For instance, as particles interact electromagnetically in such extreme conditions, the uncertainty in their positions and momenta, induced by quantum foam, can lead to phenomena like vacuum polarization. This occurs when a photon temporarily creates a particle-antiparticle pair from the vacuum, which can in turn affect the properties of the electromagnetic field in its vicinity. The foam's fluctuations can thus modify the effective charge of particles, leading to observable effects in high-energy experiments. Moreover, the interaction of quantum foam with electromagnetism could have implications for the unification of forces. Theories that attempt to unify gravity with electromagnetism, such as string theory, suggests that at the quantum level, space-time's geometry is influenced by the energies and interactions of fundamental particles. In such frameworks, the fabric of quantum foam might play a critical role in shaping how electromagnetic forces operate at very small scales, potentially connecting the behavior of light with the quantum fluctuations of space-time. As researchers continue to explore the behavior of quantum foam, particularly through the lens of advanced theoretical models and experimental setups, quantum foam, which is a concept emerging from quantum gravity theories, suggests that on incredibly small scales, space-time is not smooth and continuous, but rather is subject to fluctuations, creating a frothy, turbulent structure. This idea, introduced by physicist John Wheeler, implies that at the Planck scale, which is around 10 to the power of 35 meters, the very fabric of space-time is jagged and chaotic, filled with temporary particle-antiparticle pairs popping in and out of existence. The implications of quantum foam for our understanding of a deterministic universe are profound. In classical physics, determinism holds that, given complete knowledge of the present, one can predict the future with absolute certainty. However, the presence of quantum foam introduces a level of unpredictability and inherent uncertainty to the fabric of reality. If quantum foam means that space-time can fluctuate wildly, this challenges the notion that the universe operates under deterministic laws, because it suggests that the fundamental building blocks of reality are not stable. Instead, they may behave in ways that are inherently unpredictable, leading to a universe where outcomes cannot always be foretold, even if we knew all the initial conditions. This idea intertwines with the principles of quantum mechanics, particularly Heisenberg's uncertainty principle, which states that certain pairs of physical properties, like position and momentum, cannot both be known to arbitrary precision. Moreover, the existence of quantum foam may imply that on cosmological scales, the universe might be influenced by processes that do not adhere to deterministic laws, potentially allowing for random events at the quantum level to ripple out and affect larger scales. This could lend itself to a universe that is not strictly deterministic, but rather probabilistic, where outcomes can only be described in terms of likelihood rather than certainty. Furthermore, the implications of quantum foam might extend to discussions about the nature of time itself. If space-time is subject to quantum fluctuations, this could suggest that time is not a linear and fixed dimension, but something that is more fluid and dynamic. complicating our understanding of causation and timeline. In light of these ideas, the deterministic universe concept, which has been a cornerstone of scientific thought, faces significant challenges, as the inherent unpredictability introduced by quantum foam raises questions about free will, causality, and the nature of reality. As we explore these quantum realms, we may find ourselves reevaluating not only the laws of physics, but also our philosophical understanding of existence, suggesting a universe that is much richer and more complex than we. Quantum foam, a term coined by physicist John Wheeler, refers to the idea that at the smallest scales of space-time, the fabric of the universe is not smooth or continuous, but rather it is a frothy, This concept arises from quantum field theory, which describes how particles and forces interact at the quantum level. In this framework, space-time itself is subject to quantum uncertainties, leading to the notion that tiny bubbles of energy can spontaneously appear and disappear, creating a sort of chaotic background that underlies all physical phenomena. In quantum field theory, particles are excitations of underlying fields, and these fields exist throughout all of space-time. When we think about quantum foam, we can imagine it as the manifestation of these fields fluctuating at incredibly small scales, often on the order of the Planck length, which is about 10 to the power of 35 meters. At such minute distances, the classical idea of space and time breaks down, and the effects of quantum mechanics become dominant. The fluctuations in quantum foam suggest that, instead of a static and empty vacuum, what we perceive as empty space is actually a bubbling cauldron of activity, where virtual particles pop in and out of existence, contributing to the overall structure of the universe. This quantum foam has profound implications for the fundamental nature of reality. It challenges our classical intuitions about the universe being made up of solid, unchanging objects. Instead, it implies that the universe is a dynamic and fluid entity, where the very fabric of space-time is alive with activity, constantly shaped by the interactions of fields and particles. Moreover, quantum foam is thought to influence the behavior of black holes, as well as the early moments of the Big Bang, suggesting that our understanding of gravity and quantum mechanics might be intertwined in ways we have yet to fully comprehend. The role of quantum foam also extends to the concept of vacuum energy. In quantum field theory, even a perfect vacuum devoid of matter has a non-zero energy density due to these fluctuations, leading to what is known as vacuum energy. This energy can have significant effects on the universe, particularly in the context of cosmic acceleration and dark energy. The energy associated with quantum foam might contribute to the mysterious force that is driving the accelerated expansion of the universe, although this connection is still an area of active research and debate. Furthermore, researchers are exploring how quantum foam might affect our understanding of gravity, especially in attempts to reconcile general relativity with quantum foam. A term coined by physicist John Wheeler describes the concept of space-time at the smallest scales, where it is believed that fluctuations are so intense that the very fabric of the universe becomes turbulent and frothy, much like the surface of an ocean during a storm. As we look to the future of research in this intriguing area, scientists are eager to explore its implications for our understanding of physics, particularly in the realms of quantum mechanics and general relativity. One of the significant future directions for research is the investigation of how quantum foam might provide insights into the unification of these two foundational theories. Currently, quantum mechanics governs the behavior of the very small, while general relativity describes the large-scale structure of the universe, including gravity. Researchers are hopeful that by studying quantum foam, they might uncover a bridge between these two domains, potentially leading to a theory of quantum gravity, which remains one of the biggest challenges in modern physics. Another area of focus is the impact of quantum foam on black holes. The behavior of space-time near the event horizons of black holes is still not fully understood, and theorists speculate that the quantum fluctuations associated with quantum foam might play a crucial role in phenomena such as Hawking radiation. which suggests that black holes can emit particles and eventually evaporate. Understanding the dynamics of quantum foam in these extreme environments could lead to groundbreaking insights into the life cycle of black holes, as well as the nature of singularities, where traditional physics breaks down. Additionally, researchers are examining the potential effects of quantum foam on the propagation of light and other forms of radiation through space-time. It is theorized that the fluctuations in quantum foam could lead to observable phenomena, such as variations in the speed of light over vast distances or the creation of virtual particles that could influence cosmic background radiation. Experiments designed to measure these effects could provide empirical evidence of quantum foam, enabling scientists to refine their models and deepen their understanding of the universe. Moreover, the implications of quantum foam extend into the burgeoning field of quantum computing and information theory. As researchers develop new quantum technologies, understanding the underlying structure of space-time at the quantum level could inform the design of more efficient quantum systems, potentially revolutionizing computing and communication. The interplay between quantum foam of distance is another exciting avenue for exploration, as it could lead to advances in quantum communication networks and cryptography, enhancing the security of information transmission. Finally, as our observational technologies, quantum foam, often described as the fundamental structure of space-time at the smallest scales, presents a fascinating view of the universe, suggesting that, at the quantum level, space-time is not smooth and continuous, but rather a turbulent, frothy sea of fluctuation. This concept, introduced by physicist John Wheeler in the 1960s, postulates that these fluctuations occur at the Planck scale, which is about 10 to the power of 35 meters. Meters where the classical ideas of gravity and space-time break down, leading to a realm where quantum mechanics reigns supreme. These tiny, ever-changing bubbles of energy, or foam, emerge and disappear, challenging our understanding of reality and forcing us to reconsider what we think we know about the fabric of the universe and how it operates on a fundamental level. Now, when we think about the implications of quantum foam on space-time itself, we must consider how this concept might influence our understanding of gravity. Traditionally, gravity is viewed as a force that acts over a distance described by Einstein's general theory of relativity, which depicts gravity as the warping of space-time by mass. However, if space-time is indeed made of quantum foam, the very nature of gravity could be more complicated, potentially leading to a new theory that unites quantum mechanics with gravity, offering insights into phenomena like black holes and the mysterious nature of dark matter. This intersection of quantum mechanics and gravitational forces raises intriguing questions about the behavior of particles in extreme environments and how they might inform the broader structure of the cosmos. As we delve deeper into the relationship between quantum foam and black holes, we encounter the concept of information loss, which has puzzled physicists for decades. According to the laws of quantum mechanics, information cannot be destroyed, yet when matter falls into a black hole, it seems to vanish from our universe, leading to a paradox. The quantum foam could play a role in resolving this issue, perhaps by providing a mechanism through which information is preserved even in the chaotic environment near a black hole's event horizon. This preservation might occur through complex interactions at the quantum level, suggesting that the fabric of space-time itself has a way of encoding information, despite the apparent destruction caused by black holes. Furthermore, exploring the impact of quantum foam on cosmic inflation, the rapid expansion of the universe just after the Big Bang, reveals potential connections that could reshape our understanding of the early universe.